Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. So welcome, first of all, welcome to my class. So today we are going to do the topic that is uh, your three-phase induction motor. So in three-phase induction motor, in the previous class we have discussed about the constructional features that we have know, and we have little bit discussed about the working principle of the three-phase induction motor. So when we have discussed about the working principle of three-phase induction motor, so there we have seen that, and the application and those things we have done. So there we have seen that uh, this nowadays the three-phase induction motors are widely used. So there are some advantages regarding this. This motors is very much applicable in all over the world in case of all types of industry. The main thing is that its efficiency is high. Next, it's need less maintenance, and one more very important thing is that it has a capacity of self-starting. Now this capacity of self-starting makes it's a different from the single phase induction motor. So in case of single phase induction motors, we know that there is no uh, self-starting capacity, so make it there is a production of pulsating magnetic field. That's why there is a no starting torque is produced. So pulsating torque is producing over there, and so to make it start single phase induction motor we need a capacitor condenser. But in case of this three phase induction motor, we doesn't need any other equipment to start. So it has its own capacity in own characteristics, so that whenever supply is given to the three phase induction motor, the motor starts rotating. So how it starts rotating? So the concept of this starts rotating is known as a rotating magnetic field. So in case of three-phase induction motor, there basically magnetic field is generated that is rotating in nature, and due to that the rotor itself starts rotating due to the force provided by the magnetic field. So in today's class we are going to understand how this rotating magnetic field is generated, and due to which this three-phase induction motor is a self-starting machine. So let us start. Yes, first we are starting with the introduction part. So in the introduction we are going to just recap what is a three-phase induction motor. So in case of three-phase induction motor, we know that it is a three-phase supply must be given to the machine, as it names as it is a three-phase machine, and it has two parts. One is the stator, one is the rotor. The stator is slotted, the inner periphery of the stator is slotted, and there we make some windings, and those windings are connected to some sort of electrical supply, and that stator winding or field winding generates the magnetic field, which is actually rotating in nature. And inside that stator we have a rotating part that is known as the rotor. So rotor, already we have discussed in the previous classes, rotor can be of two types. What are the types? So first type is the squirrel cage type rotor. We have one. Second type is rotor is given, we know that slip ring type rotor. So in case of squirrel cage rotor, it is used for the lower power range machines, and it can be used for the fixed speed. So as it has a cage type rotor, so we cannot add extra resistance to this particular rotor circuit, so we cannot control the speed of this particular squirrel cage induction motor. So already we have discussed this one. And in case of slip ring, what we have discussed previously, that in case of slip ring induction motor, over the rotor we have three rings. Those are known as the slip rings, and over there the terminals of the rotor winding is connected, and there we can connect the external resistance. So we can say that the slip ring induction motor can be used where we need a variable speed, and for the large machine we actually use the slip ring type induction motor. So these things we have already discussed, and now we will try to understand how this rotating magnetic field is generated. So first, coming to the figure description, so follow my pointer, it is very interesting point. So this section, this outer section is the rotor section, stator section, and inside that this section is the rotor section. So outer side is the stator section, and inside that we have the rotor section. In the stator section, what we have in the stator section, we have the inner periphery slotted, and in between that slot we have the windings and in that slot we have the windings, and in next case we have uh, rotor. Over the rotor we have copper bars, and that copper bars are actually magnetized, and that is generate some torque value, and due to that torque actually it starts rotating. Now let us see what is the principle behind this one, so that it is start generating. So for your better understanding, so here step by step pictures are given, so that you can very good understanding should be generated to you. So what is there? So this is the, see, there are four pictures are given. So as we know, there are three phase supply is given. Okay, one more thing I want to add over here, it is that three phase balance supply is given, and three phase balance supply means each phase are separated from each other by an angle 120 degree. So all phases are shifted from each other and all has the same magnitude. So balanced supply is given, has 120 degree phase shift made between any two phase, and it has equal magnitude. So this kind of supply we have to give to the three phase induction motor, then only we can say that there will be generation of rotating magnetic field. Okay, so again follow my pointer, phase 1, phase 2, phase 3, three fixtures are given. So for your simplicity, here we have considered three colors for the three phases. So one is the red color is showing over here, and for your simple understanding, we have considered over here two stator slots, two stator pole actually. So it is showing one phase, this phase 2, this is denoted by this white one, and the phase 3 denoted by the yellow one. Now if we combine these three, how it look like, the last one is the that thing. So like this way the winding is done in the three phase induction motor. So where the three phase supply is given to the opposite status slot, and we make the output. Okay, so this is the connection. So here for the simple understanding, we have considered one wire for each phase, but in real one we have the thousands of a wire in each phase. Okay, so the concept or visualization of that concept is like this, that the three balance supply is given in a three phase induction motor, and now all are shifted from each other by an angle 120 degree. Say for um, understanding, we are considering that the rate phase is started from xy axis 0 0 terminal, and from that 120 degree lagging behind phase 2. Again from phase 2, phase 3 is again lagging behind by an angle 90 degree. So like this way three phases are shifted from each other. Okay, and now if we think like this way, that if we consider the, if phase 2 is a reference phase, then we can say that phase 1 is leading from phase 2 by an angle 120 degree, and phase 3 is lagging behind from the phase 2 by an angle 120 degree. Like, correct? If we consider phase 1, phase 2 and phase 3 is lagging behind. If we consider phase 2, from that phase 1 is leading, phase 3 is lagging behind, and if we consider phase 3 as a reference, then we can say that phase 1 and phase 2 all are leading, correct? So these are the thing, this is the just concept. Okay, and now this thing is a very important thing. So first, before understanding this one, I want to tell you that just follow this, follow my pointer, and I am pointing this waveform where three phases are represented by pink, green and yellow lines, and they are shifted from each other by an angle, 120 degree. Now, very interesting. Now say, if we consider any instant, what is the instant? So they are different. This, follow my pointer, these straight lines are placed over here. These are the different instant. See, what is the instant? How many instant are there? 1, 2, 3, 4, 5, 6, 7. 7 instants are there. So that means three-phase supply is given to the induction motor, and we are viewing what is the nature, what is the characteristics of the three-phase induction motor when 7 instances are calculated, when instances are inspected. So when the 7 instances are inspected, so there we can find out some interesting characteristics. What is the interesting characteristic? So again, come back to the waveform analysis. So if we come to the position 1, so there we can say that there's yellow phase is in the positive half, and this green and pink is in the negative half. Like this, if we come to the phase, that means the instant 2, there we can say that this yellow and pink phases are in the positive half, and this green one is the negative half. Like this way, phase 3, phase 4, phase 5, say phase 5 again, the instant 5 we are taking. At that time, green is only in the positive half, pink and yellow in the negative half. 6, again 6, 6, what is happening with the 6? With the 6, green and yellow in the positive half, and this pink is in the negative half. And in the last, in the 7, it is showing us that this yellow is in the positive half, and 7, the green and pink is the negative half. Now I think you have understood that which one in the positive half, which one in the negative. This is very simple. It is school level physics. If this is in the higher one, it is a positive half, and in the lower one, it is a negative half. Now, from this thing, what we are going to conclude? We are going to conclude nothing. We are going to um, just check according to the positive and negative half how the direction of the current is changing. Now, with the change of this direction, the generation of the magnetic field is changing. Say there is a solenoid, and we are giving supply from this side, and it is going out from this side. So can we say that the current entering from here, it is leaving from here? The entering side, we know that there is a north pole generation, and the leaving side there is a south pole generation. So when current is entering from here, there is a north pole generation, there is a south pole generation. Now, when this current is in the negative half, so we are considering AC current is supplying. So when it is at the positive half, current is entering from this side and it is leaving from this side. And when it is in the negative half, that same current, so current will enter from this side and it will leaving the circuit from this side. So at that time, what will happen? North pole will generate over here, and south pole will generate over here. That means, what is the conclusion? The conclusion is, when the current is at the positive half, so say if there is a north pole, there is a south pole, and when it is in the negative half, the reverse case will happen. That means the poles will exchange. Here is the north pole, here is the south pole. So like this way, see, now check the point 1. At point 1, yellow one is the at positive half, so it will generate north pole and south pole, and opposite to the other two phases. See, other two phases are the negative half, so its direction of flux will be opposite. So like this way, um, the phases are placed over here. See, this is 1 1, the phase 1, this is phase 2, and this is phase 3. So the phase 1 flux direction is this, phase 2 flux direction is this, phase 3 flux direction is this. So like this way, so you just check, you just follow what is there. So here 3 north poles are presenting over here, and 3 south poles are presenting over here. So three fluxes are acting such a way that three north poles are generated over here, three south poles are generated over here. So what is the resultant characteristic in middle one? So there is a three north pole, there is a three south pole. So in between that one there is a resultant flux. There is a north, there is a south, that is the resultant flux. Now see in the point 2 it is changing. Now north pole is shifted in the clockwise direction and south pole is shifted in the anti-clockwise direction. So the now the resultant flux, so first initial resultant flux is this, next case it is shifting like this. Now say point 3, in the point 3 it is again shifted. So first position this, second position this, third position is this. So number point 4, so this is the point 4, see exactly the opposite. So first, second, third, fourth. So this is the fourth location where the resultant magnetic flux is changing its location. So now it is the second case, 5 6 7. So if we just follow all the points, 7 points, we can say that the resultant flux is changing first position, second, third, fourth, and fifth, sixth, seventh, like this way it is changing. That means the resultant flux, so due to the three-phase supply to the stator winding, whatever fluxes are produced, that flux is rotating in clockwise direction. Okay, and now some fluxes are rotating in clockwise direction, correct, like this. And if we put a rotor inside that, it will face some force over it, and due to that force the rotor starts rotating. So this is actually the rotating magnetic field. So the magnetic field what is given supply to the stator, it itself rotating, and when we plot a rotor inside that, and it faces some force, then due to that force and due to that torque generation it starts rotating. Okay, so that's why it is a self-starting machine. It doesn't need any other equipment or components to start over. That's in three-phase induction motor. This is the very important characteristic. That means the poles are generated over the stator, it is changing continuously, and due to this the rotor always starts always rotates. Okay, and the speed at which this flux is rotating is known as the synchronous speed. And always remember, in case of induction motor, three-phase induction motor, the rotor speed, the actual rotor speed that we can see, but we cannot see the flux speed. So the rotor speed is always less than the synchronous speed. That means that's the speed of the flux. That means whatever is the speed of the flux and the rotor speed, there is a difference. Because if both are rotating at the same speed, so there will be no relative velocity. And if there is no relative velocity, there will be no production of the torque. If there is no production of the torque, so there will be no rotation of the rotor, so the rotor will stop. So that's why it is the inherent property of the induction motor, so that the rotor always rotates less than speed of the synchronous speed, and that's why it is known as the asynchronous machine also, asynchronous motor also. Okay, so now we have seen the working principle, how it is works. Now we are going to see how much flux it is generated in the three-phase induction motor. Yes, production of the rotating magnetic field. So now we are saying that three phases we have to consider, and each phases are shifted from by an angle 180 degree from each other. So now here I have considered that three phases. Phi 1 is its value is any instant flux equation. We know phi is equal to phi max sin omega t. That formula I have used over here. So phi 1 is equal to phi m sin omega t. Okay, next one is phi 2, definitely 120 degree apart. So phi m sin omega t minus 120 degree to 120 degree, and phi 3 is again shifted from phi to again 120 degree. So phi m sin omega t minus 240 degree. Okay, so there are okay, this is the phasor diagram representation of three fluxes, and this is the waveform analysis of the three phase that actually apply to the three phase induction motor. Now coming to the analysis part. Okay, so coming to the analysis part, so at case 1, case 2, case 3, different things we can see over here. What is that? See, um, there are three phases shifted from each other by an angle 120 degree. But between any two, when between any two phase, when it is crossing the zero line, so what is the difference between these two? So we can say that at different times, different phase angle, we can say that what is the, we want to find out any time at any instant what is the value of the total flux. So case 1, we are using that theta is equal to 0 degree. So if it is theta is equal to 0 degree, put that value in the equation. So that means theta means the omega t is equal to 0 over here. So sine 0 is a 0, phi 2 is a omega t is 0, so minus 120 degree. So minus 120 degree is 0.86 is phi m. So if I like this way, if we add those things, we will get phi 3 is equal to phi m sine minus 240 degree, that is equal to the 0.86 is phi m, correct? So these are the three phases we have. Now the resultant flux will be the summation of this vector summation actually of these three fluxes, phi 1, phi 2 and phi 3. So this is the diagram where we can say that this is the phi 3 axis, this is the phi 2 axis, and the phi 1 axis is does not present over here, as see that has no angle. So the resultant of this two is this one. So what is the value of this resultant? So if we just make a geometry over here, so we can find out that resultant flux value, this value, so from the geometry we have done in three-phase chapter. So from the geometry chapter we can solve this one. So it is the value is 1.5 phi m. See, follow my pointer, it is showing that this is 1.5 phi m. Now same thing we are repeating again, 6 degree shipment of the flux. So if we change the 6 degree shipment of the flux, the values are like say sine 60 degree, sine minus 60 degree and sine minus 180 degree, that is equal to 0. So again here we have the two phase, that is has one is positive 0.866 and one is the negative 0.866, and due to that we have two phasor, and it has a resultant flux value, and it is again coming 1.5 phi m. So like this way, if we do continuation at 120 degree, 180 degree, at 240, 300, 360, and each and everywhere we are going to find out. See, just let me check. Case 4, the theta is 180 degree, so at that time also the value is 1.5 phi m. That means it is very important point that the resultant flux is 1.5 times of the maximum flux. So that's these are the different many advantages for which that for which the induction motor is very much popular nowadays. That means whatever maximum flux is produced, and the resultant flux is 1.5 times of that maximum flux. So it is very advantageous for the three-phase induction motor. So this is all about today. So in this particular class what we have studied, we have seen that the little bit constructional features, then we have elaborately discussed about the rotating field, how the rotating field is generated, how the flux is rotating in the clockwise direction, and due to that how the torque is generated over the rotor, and due to that the rotor is a self-starting machine. And then we have seen that how much resultant flux is generated inside this three-phase induction motor. That value is 1.5 times of the maximum flux. So those things are very important things. I think I have made you clear. So this is all for today. Thank you.